here because this is very, very important. Okay? So this is our older friends about this orthogonal carding speed. This is uncolored chip thickness, big angle, clearance angle, or called the relief angle. So here is the chip formation. About chip formation, we have velocity, cutting speed, and we have VC is the chip velocity along the big face, and VS is the shear velocity along the shear plane, and the shear angle is the phi. So we also know based on if we have the cutting forces F and this is N, and these two guys form this is the resultant force R, and so this R can be decomposed by many ways as long as the two junctions are orthogonal. For example, this R can be decomposed into N and F, and also can be decomposed into IFC cutting force and the thrust force. Also here, so here this is Fs. So this is Fs along this shear force. This one is perpendicular to this shear angle. So this. Then today we talk about the tool condition monitoring. So there are several the tool condition can be monitored, and there are several ways. One is a direct method, another one is an indirect method. So based on the noise, based on the signals, when we cut, we know that when we cut some material, and we will have some signals, right? Some of these signals are, for example, the acoustic emission sensors. I used before I came to this country, acoustic emission sensor, and also I use this as a current sensors and to measure the current, because when the machining is carried out, the current, the signal changes, current changes. There are a lot of other signals that will be changed if there is a cutting. And based on this, the changes of the signal, and we can monitor the tool condition. Okay, and so two direct methods and indirect method. Direct method means that we can observe this condition of cutting tool. This includes optical measurement of where to use the microscope, or where by periodically observing the changes in the profile of the tool. The profile of the tool means that the ring face, if there is the craters on the ring face, or the flank wear. Flank wear means that the wear along this flank surface. These are called the profile of the tool. So, on direct method, this use your eyes and to look. The second one, as I said, you can just based on signals, okay, and correlate the tool condition with the process variables such as force signal, the force, if the cutting condition, if the cutting, and definitely the force will be much better than it is before the cutting begins. The power consumption, right? The temperature rise, and surface finish based on the machine surface. Usually, the tool condition affects the surface finish substantially. Whenever you just want to look at the surface finish, and you know what kind of conditions your tool is. So variation and other variations, for example, acoustic emission technique. So this is what I used before. So I have done this one before. So yes, we have the commonly used sensors include the force sensor, the power sensor, the temperature sensor, and surface finish. And you can use this is ICEM, and you can use this is a profilometer, and other sensor vibrations. This is vibration sensor, okay, and also the acoustic emission sensor. If I ask you and tell me some sensors that people are using to monitor the tool condition, so you can tell me force, power, temperature, and surface finish and vibration, and also the acoustic emission technique. So this is the tool condition. So tool condition. Why tool condition is important? So the tool condition non-intrusive to the machining operation. So accurate and repeatable in signal detection, resistance to abuse, and typical shop floor environment. So cost effective. If you can do this tool condition monitoring, and you can have so this kind of benefits. So non-intrusive to the machining operation. So you do not need. You can just monitor the tool condition. You don't need to stop it. Okay. You don't need to just stop it when there's a catastrophe happens. So accuracy and repeatable in signal detection, resistance to abuse and typical shop floor environment. So if you can monitor the tool condition very well, so you can just change the tool on time and to make sure you have better surface finish before the tool totally is worn out. So cost effective. This is cost effective. So this can reduce the cost of machining, because if the tool is worn too much, the workpiece, the finished products will not be usable. So acoustic emission and wear. Do you guys know what is acoustic emission? Acoustic emission means that if there is a large deformation, right, for our case, large deformation because the tool cuts the material, and there is a crystalline. This is a crystalline move. This location is the move. So based on this is a microstructural changing, and there will have acoustic emission. Acoustic emission, and usually the frequency is very high. It's about 50K, right? 50K hertz. 50K hertz to 1 megahertz. So this is very high. Let me write down. So acoustic emission is also called AE, right? So this is about 100K hertz and to about 1 million hertz. So this is a high frequency. So if we use acoustic emission sensors, and we can just reduce the effect of this lower this noise signal. Noise signal, sometimes if something happens in the machine shop, and this low frequency noise signal will be captured. However, if we use AE signal, acoustic emission sensor, and so we can just eliminate this kind of, because AE sensor cannot detect the low frequency material signals. So you can see here is the machining time. This is the mean stress. So this is between the mean blank wear, okay, maximum critical wear and acoustic emission noise generated during cutting as a function of machining tool. So you can see as the time goes, if there is a blank wear is the blank wear with have progressive blank wear or progressive critical wear, and so this is acoustic emission sensor. The signal will be increasing. So this technique has been developed as a means for continuously and indirect monitoring wear rate in this various cutting process without interrupting the operation. So this is AE has been used very successfully. Then we talk about surface finish. Why surface finish is important, and the surface integrity. The surface finish mainly talk about the surface finish of the machine tool, machine material, machine surface. Okay, describes the geometric features of the surface. So this is a dimensional. This is a geometric features. So surface integrity is pertains to the properties such as fatigue life and corrosion resistance. So I get to sweating. Sweating. Huh? Very warm, right? Not because I'm sick. Yeah, I just want to make sure everybody is sweating. That's fine. Okay. So such as fatigue life, properties, and corrosion resistance, which are strongly influenced by the type of surface produced. Surface integrity, microstructure. Surface integrity include the hardness, microstructure, This is the phase transformation. So this is called surface integrity. Can I write down? The first surface integrity includes hardness of material, right? Includes the microstructure or nanostructure of phase transformation. The material change, metallurgical change is called surface integrity. Do you know integrity, right? Is integrity? What does integrity stand for? I mean, what does integrity mean? Change, something change. Right? So the factors that influence surface integrity include definitely temperature. Temperature is a very bad thing. The temperature is generated during the processing. So the temperature we have, I told you, we have acronym HAZ. HAZ means that the heat affected the zone, right? The heat affected zone. So because when we cut the material and we use a lot of energy, so this a lot of energy will be converted into heat, and this heat is bad because it will adversely change the surface integrity of the machine surface, and also the soften the tool and makes the tool is much easier to be worn out. So the temperature is bad. Okay, if you can invent some manufacturing processes that do not change the temperature too much, that'll be awesome. And second one is the residual stress. And why the residual stress can affect the surface finish. So residual stress means residual stress. Why? Because we have two different kinds of residual stress. One is compressive and one is tensile, right? The tensile residual stress is bad because tensile residual stress facilitates the crack initiation and crack propagation. So that changes the surface integrity. So compressive residual stresses are good because compressive residual stresses prevent the crack from initiation and from propagation. So write down here, okay? So metallurgical transformation is a phase transformation, metallurgical. For example, this is the steel. So are you taking the material science class? No? Are you? Okay. So if we are taking this is you know what is the metallurgical transformation? It's very the steel. For the steel, the common steel, and they call it steel, but they have multiple phases. You know the phase. What's the phase? You know the phase, right? Phase means that the same material, same element, same material. However, if these guys they have one different either physical property or this is a chemical property, we call these two guys are two phases. For example, the water, H2O. H2O has three phases. Water, called this is liquid water, the gas, vapor, and this is also the ice, right? So can you tell me what's the difference between these two guys? Only the shape. Is it solid, right? So one is solid, one is liquid, one is gas. And even look at these different states, they are three different phases. So as long as one either physical or chemical property is different and different phases. Right now, okay? So plastic deformation, tearing and cracking of the surface. I want you guys to know, okay? Surface integrity includes these things. Surface integrity include, let me write down, hardness, residual stress, and this is a phase transformation. So this is called surface integrity. The surface integrity meaning hardness, residual stress, phase transformation, and also there's some plastic deformation. So they just change the mechanical property. Wait, I'm gonna ask you in our the midterm. Hardness is not included on the slide, but you should know definitely hardness is important. Well,
did you also want us to know about? I think you mentioned microstructure earlier.
yeah, microstructure actually is this one.
Okay.
Microstructure. Microstructure is you use this one. Microstructure is more general, right? So these two guys can be used interchangeably. Microstructure, something with very good. So you can see the temperature is very important. Temperature can change the hardness, can change the residual stress, can induce the base transformation, and also process the temperature is bad. So here is a surface finish for different machining. The rough cutting, the casting, forming, machining. This is machining we are focusing on. This advanced machining. Advanced machining includes chemical and EDM and electrical discharge machining. And we will talk about this one later after we finish these fundamentals. Laser machining, we will talk about this one also. Electron beam machining and electrochemical machining. So this is a surface finish. So we are focusing on this one for machining. So, this is the roughness. This is roughness. Roughness definitely is a surface finish. Okay? And as I said, surface finish is the geometrical feature, and surface integrity is the mechanical property change. Be very careful. And they are related, but different. So surface finish and the surface integrity. So these two guys are always talk together, right? So in machining, and some consumption remind me what the BOE stands for? Huh? Yes, the built-up edge. The built-up edge has the greatest influence on surface roughness. Surface roughness is a surface finish, and since it has significant effect on modifying the tool, because the BOE is part of the workpiece material is attached on the rig face of the tool, right? So because that additional part, so the tool profile is changed. The rig face is changed. I'm going to show you. Ceramic and diamond tools generally produce better surface finish, and because of their much lower tendency to form BOE. So because the ceramic and diamond, these two guys have very low affinity and with the commonly used material. A tool that lacks the sharpness has a large radius along its edge. So sharp, I told you, the sharp tool. So if we have a tool, okay? So usually, so there is a edge radius. This is called edge radius. So strictly speaking, and so these are two lines. We do not have the sharp angle. Sharp angle is bad. It's practically is bad. So we have this edge radius. Okay. Even though the edge radius is very small, but still have edge radius. However, if this is for some reason this edge radius is big, they have a bad, very bad influence on the surface finish. So for the BOE, right? Suppose we have this is my BOE. So this is my original tool. This is my BOE. You can see in this area, this neighborhood, the tool shape is changed. The tool lacks the sharpness means that it becomes dull. It has a large radius along its edge. So this is surface in finish. So here, surface introduced on steel in machining as observed with SEM. Have you guys ever used SEM? Question?
Yes, you said that it doesn't have a radius that's bad, right?
Yeah, if it's sharp, if this angle is really sharp, it's bad.
What happens if it's too sharp? Will it dig itself into the material?
Yeah, it will be broken. Because it is sharp, here it will be very weak. The strength is not high, right? Very sharp angle.
Yeah.
That's the reason we usually have the radius. You look at here, this ICEM, so this is the scanning electron microscope is very good, and to see this surface finish. So for this is for Turner surface, and for this is surface produced by shaping. So for these two SEM images. So here and shows the Dow tool. The Dow tool means the Dow tool. That means radius it becomes bigger in orthogonal carding. This is exaggerating. Okay, this is not very true, but for the visualization effect. Note that at a small depth, see if this depth card, okay? At a small depth of card, the Ricci angle can effectively become negative. See, if this is my depth of card, and then from here, so this from here, this is my tool. I go here, so this will be my Ricci angle. Ricci angle is going forward. That means Ricci angle is positive. I'm sorry, negative. Negative means that so this tool is going to be pouring on this surface, not cutting. That's all right? Question, okay? So here, if the depth card is increasing, for here, if this is totally fine. But if we just card so thin layer, here is my tool, right? So will be my tool. This will be my tool wrinkle face, right? My tool wrinkle face, and based on the definition of Ricci angle, and how to measure the wrinkle face. Go here, right? This is my wrinkle face, and then the positive. This is vertical. The Ricci angle is measured between this vertical line and your wrinkle face. And here is negative. We know that the wrinkle face, so this is the vertical line, so this is my tool, face. So here is a positive. However, if I have this kind of tool, suppose I use dotted line. If I this tool, this is another tool. So this one, the tool face, this is the vertical line. So this is negative. This is positive. So this is my Ricci angle for my second tool, and this is Ricci angle for my first tool. See? Even though nominally and your Ricci angle is positive, right? So at vertical line, this is my wrinkle face, so this is a positive Ricci angle. But here, in effective Ricci angle becomes negative. Negative means that this tool is pouring, it's being poured, on the surface. Pouring means that this is not cutting, just mostly the compression. So I may ask you, use your own language diagram to show me how the Dow tool affects the surface finish. Just use what I just told you. Question? And then we look at this terminology in turning. I introduced this one last time, but today I want to tell you again. So this is the turning. So this is exaggerated also. If we have this kind of the machining mark, that is very bad. Okay. So just for visualization, this is the tool. This is a tool holder. So this is a shape. And so this cylinder is rotating. And so in this way, like radially, this is called depth of card. This is for 3D. But for feed, in this direction, it's called feed. And also, there is a statement, the feed in turning. Right? Feed in turning is equivalent to the depth of card in orthogonal carding. Last time I told you. Right? So what's the difference between this one and orthogonal carding? Somebody use his or her own language to tell me. Well,
I think for diagonal cutting is theoretical. It's not actually possible, but it would be if the feed size cut the entire It's like if it was a hollow.
Yeah. Okay, that's great. So if the width of my tool is bigger than the tool width, than the workpiece width. For this case, the difference between this one and orthogonal cutting is that if this guy is a hollow one, okay? Hollow one means that I don't have this yellow part, this one, and the thin wall is this thin wall, cylindrical. This is thin wall cylindrical cylinder, hollow cylinder. So if you cut this one, if this workpiece is thin wall cylinder, that is very close to the orthogonal cutting. So then machinability. If you work in this manufacturing community, and you might be hearing from the machinability. So machinability means that the ability of this material to be machined, right? So this is literally. What does that mean? It means the following ways. Machinability of some material means that the surface finish and integrity of the machined part for this material. Different material, and even though you use same parameter, same machine, and you will get different surface finish and integrity. A second one is a tool life. If this material is very, very hard, right? And if you use the same tool will be worn out very, very quickly. So this is tool life is one of the machinability. The third one is the force and power requirement. And how much force, if you want to machine this material, and how much force you need to apply, and what is the requirement for the power consumption. And the last one is shape control. And shape, if you must, what kind of shape mobility, and for this is a new material. I told you, if the chip is continuous chip is bad, right? Very, very dangerous to jeopardize people, operators, and also scratch the machine surface. So this is the chip is bad. You need to use a chip breaker or any other kind of mechanisms to break the chip on time. So this is machinability. So the skills. Skills is are commonly used material. And that is still machinability skill, right? So here is some statements. Lead is added to molten steel and takes the form of dispersed fine lead particles. So during machining, the lead particles are sheared. These are particles. Right? During machining, definitely. So this is molten steel. I add these lead particles. Then then after some time, so this molten steel solidifies and then cool down, and then I can machine. So during this time, during the machining, the lead particles are sheared and smeared over the tool chip interface. Because of their low shear strength of the lead particle acts as a solid lubricant. Right? So lubricant means that it can just facilitate the relative motion between the chip and the rig face. So this behavior can be verified by noting the presence of high concentration of lead on the tool side face of the chips. If you use the EDS, EDS is to check the elements, the existence of elements. One machine lead is skill. In addition to this effect, okay, it is believed that lead probably lowers the shear stress in the primary shear zone, thus reduce the cutting force and power consumption. So this is first one. This guy behave like a solid lubricant. Second is a lower the reduce the cutting speed and power consumption. So lead skills are identified by L between the second and third numbers, such as 10L45. Okay. So if I ask what kind of roles the lead particles play in leading the steel. Two things. First, storage the lubricant. Second, reduce the cutting forces and torque subject. Right? So this is the two key words. Reduce the cutting force and act as storing the lubricant. So this is lead. Definitely lead is poisonous to fuel. So this is for lead in the steel. And second one is sulfurized and re-phosphorized steel. So sulfur is another element. Sulfur in steel forms manganese sulfide inclusion of the particle, the second phase particles, and which acts as a stress resistors. Okay? If you have taken the mechanical solids class, the stress resistor that causes stress concentration, and in the primary shear zone, as a result, the chip produce a small and break up easily because the stress resistor, and this improves machinability. Okay. Phosphorus, another element in steel, improves machinability by virtue of this is strengthening the ferrite, thereby increase the hardness of the steel and producing less continuous chip. So I will ask you, what role the sulfur plays? Right? So plays that chip produce a small and break up easily. As I said, if the chip is continuous, it's bad. Ideally, I want the chip to be small as possible. Okay? Make sense? Okay. What is the role the phosphorus plays in the steel to improve the machinability? By stressing the ferrite, thereby increase the hardness of the steel and producing less continuous chip. Here is the key word. Right? I will ask you, what is the lead? What's the role for lead? What's the role of sulfur? What's the role for this phosphorus in the steel? And to improve the machinability. So next one is a calcium dioxide, deoxidize the steel. So oxidize the flake of the calcium alumina silicate. So this one, and they are formed. And these flakes just like the snowflakes, in turn lower the strength of the secondary shear zone. And what is the secondary shear zone? Secondary shear zone is the tool-chip interface. Okay, and tool-chip interface is the secondary shear zone. The primary shear zone is that line. Two shear zones. Primary shear zone along the shear angle. And secondary the shear zone is a tool-chip interface. Reduce basis friction and wear, and thus temperature. Right? Consequently, this causes less crater wear of the tool, especially at high cutting speeds. So this is people intentionally end something in the steel and to improve this machinability. Effects of other elements on machinability of steel, aluminum and silicon. In fact, aluminum and silicon are bad, right? Because these elements combine with oxygen and form aluminum oxide and silicate, and these compounds are hard and abrasive, and thus increasing tool wear and reducing flexibility, machinability. So if the tool wear increase, machinability is bad. And this is the tool wear is one of the indicator of machinability of the material. And second one, the carbon and manganese. They have various effects on machinability still, and depending on their composition. As the carbon content increases, machinability decreases. However, plain low carbon steel, this one can produce poor surface finish due to forming of built-up edge. Okay? Built-up edge is bad. Other alloying elements such as nickel, chromium, and molybdenum, along with vanadium, can improve the property of steel, generally reduce machinability. So if the property of the steel is improved, that is the machinery with that, right? For example, this is the titanium. Titanium is very, very tough. No, right? Titanium is very, very tough. In the very, very important applications, people use the titanium. But titanium's machinability is notoriously bad. Right? So we had an experience when we use the lathes to cut the titanium. The workpiece called fair. The workpiece called fair. No, because the thermal transfer properties of titanium is very bad. The lot of heat cannot be dissipated at one time. Temperature goes up and then exceeds the critical value, the called fair. It's bad, very, very bad. Even though this is titanium is a valuable machine, very valuable material. The cast steel are not abrasive, although their machinability is similar to that of rod steel. The tool and die steels, right? Tool and die steels. Look at their application. You know the hardness of them is very, very high. I think a very, very difficult machine usually require a kneading prior to machine because of their extremely high hardness. Machinability of most steel is generally improved by cold working, which reduces the tendency of built-up edge formation. Okay? So this is, this is fact. Cold working of the workpiece can reduce the tendency for built-up edge formation. The last one is austenitic stainless steel. So you will have better understanding after you finish the learning the material science. A generally difficult to machine, so chatter could be a problem. Chatter means the vibration of the machine, either the whole machine or the tool holder, which necessitates the use of machine tool with high stiffness and damping capacity. So this is austenitic. The ferritic steel have good machinability. Martensitic, the speed, the hardness is very high. In abrasive, tend to form built-up edge and require two materials with high hardness and resistance and to critical wear. So precipitation hardening stainless steel are stronger and abrasive and thus require hard and abrasion resistant to material. So this is a basic. This is the machinability of the commonly used the steels. So for other various metals, aluminum is usually easy to machine. However, the softer grades tend to form built-up edge and thus develop poor surface finish. So built-up edge is bad. Sometimes even though it can protect the tool. High cutting speeds and high relief angle are recommended. Right? So rod alloy with high silicon content as cast aluminum alloys may be abrasive and hence require harder tool materials. And dimensional control may be a problem in machining aluminum, and because of its low elastic modulus and relatively high thermal coefficient expansion. So aluminum is a commonly used material also, but the pure aluminum is useless. It's almost useless. Green cast iron generally machinable but are abrasive. The green cast iron. We have free carbonates in casting reduces machinability and cause tool tip or fracture. The tool tip and the tool break, and thus requiring the tools with high toughness. Nodular and malleable irons are machinable using hard tool materials. Nodular and malleable irons, they are another. This is the iron. Okay, so here are the other alloys: the cobalt-based alloy, rod copper, magnesium, molybdenum, nickel-based tantalum, titanium, and tungsten. All this is given here. Okay, and you should know that the titanium here. This titanium is as a very commonly used material now, has poor thermal conductivity, lowest of all metals, as people know. So causing significant temperature rise and formation of build-up edge, thus it can be difficult to be machined. For titanium, people usually use the thermal assisted or laser assisted to improve the temperature. As the temperature is improved, and then suddenly the hardness will be lower. The tungsten is brittle, strong, and very abrasive. We know tungsten carbide that's for the tool, but this tungsten is the pure material. So this tungsten is usually used in the lead bomb, right? In lead bomb, the traditional lead bomb, not carbon. Perfect. Also thermoplastic, thermostatic, and this is metal matrix and ceramic matrix composites. So there are a lot of materials. I'm not going to read this one, okay? And I talk about the steels, about the other commonly used metals, and the other new materials. Then we talk about thermally assisted machining. The thermally assisted machining, they use the heat, such as torch, high energy beam, or plasma to improve the temperature. So why we need to improve the temperature? The temperature is increased, and the material can be softened. And then we talk about this oblique cutting. This is oblique cutting. You can see what's the difference between oblique cutting and this orthogonal cutting. Can somebody tell me the difference? Difference is that here, so this is my cutting edge, okay? This cutting edge, for my orthogonal cutting, this cutting edge is perpendicular to the cutting speed, cutting direction. But here, no. So here is the angle, this is angle I. This is called oblique cutting. As a top view, this top view is I here. So this is shapes, the types of shapes produced with different inclination angle. So this is I. Is called inclination angle. And we're done, please. I is called inclination angle. You see, different inclination angle will result in different the chip morphology. And then we talk about right hand cutting tool. So now this time, this tool is the cutting tool we usually use. This is a tool holder, right? And this is a tool holder. There's a lot of things. So this picture will appear in our later. And I'm going to erase all these labels and ask you to label this tool holder. So there is axis. This is cutting edge. This is and cutting edge angle. So this is set Ricci angle, right? And for the we have Ricci angle, we learn Ricci angle for orthogonal, but this is 3D. We have set Ricci angle, and we have this face, this is cutting edge. We have another back Ricci angle, right? So here is the nose radius, and here is the flank. So this is the set relief angle. So this is a set cutting edge angle, and here is a clearance angle or end relief angle. This a lot of angles here. This is a tool holder. Clamp, screw, clamp, insert, we change insert. And underneath the insert is the seat or the shape. Here we talk about this one is a 3D view, and then we talk about this is a 2D view of cutting. So for this end view, so this is a set Ricci angle, still Ricci angle. So this is cutting. So this is a vertical. This is a line, reference line, and so this is the Ricci face. So this is the Ricci angle. The set Ricci angle. Still, this is the reference line, and so this is a Ricci face, and this is the set. Relief angle. So this is a flank of the face. So look at this one. This we call the set view. And set view we have this is a wedge angle. So here is rig angle. Okay, this is rig angle. So this is my rig face, and so this is my rig face, and this is my reference angle. So this angle is the back rig angle. So this is edge relief angle. So here, so this is my edge, and so this is my reference. So here is a relief angle, edge relief angle. The top view, rig face, nose radius, nose angle, this angle, nose radius. So this is called set cutting edge angle, right? So this one is a new one, cutting edge angle. So here and cutting edge angle. There are too many angles. I'm confused also. Okay, all right. This Wednesday I'm going to ask several students to come here to tell me what these angles are. But at that time. Okay, very, very important. We need to know these angles. So I'm going to, under today's session, and as I said in my announcement, using the cameras, if we want to get this as a credits for homework 3 and homework 4, and I still give you some time to do it, okay? But it's totally optional. I didn't tell you, but the homework will contribute a lot of the fraction for the final grade. If you don't keep missing this.